Now there's one little tricky thing about working with mechanisms, because as you saw in my first example, very often the mechanism for the reaction shows what's called an intermediate. Here's another example, an overall reaction here, two proposed steps. By the way, all mechanisms aren't simply 2 steps. Some of them are 3 or even 4 steps. It's just that all my examples happen to be 2 steps. But you can see that in this particular, I didn't circle it, but again we have an intermediate substance, this NOCl2, which is immediately consumed in the next step. So now we're going to see what we can figure out about this mechanism. And the question that we're trying to answer is, if we look at the mechanism, what is the overall rate law? You can actually figure this out because of the idea that the slow step rate should be the rate of the overall reaction. So you can either do one of those problems where they've given you several different experiments to work through and divide and figure out what the rate law must be. We could also figure out the rate law using the mechanism information, because we're going to base it on this red idea. So I look up above, I see that step 2 is identified as the slow step, and I write out the rate law. Okay, the rate of step 2 is equal to K2 times NOCl2 times NO, both to the first power. That's the rate of step 2. The problem is I can't really answer the question yet, because NOCl2 is an intermediate substance, and I don't want my overall rate law to contain anything that's intermediate, anything that would just cancel out of the equation. So is there anything I can do about this? I can't really answer the question yet. You might think, well, no, it's wrong, it doesn't match. But I really don't have enough information yet to figure that out. So what I have to do is I have to see if there's a way that I can kind of algebraically, mathematically deal with this intermediate. And you can do that because of this first reaction here. You see the double arrow. This indicates an equilibrium situation, which we're definitely going to talk about. But what it also means is that this reaction has 2 different rates, a forward rate and a reverse rate. And as this has been studied, the double arrow is telling us that the reactions are happening at equal rates. Look down here. The step 1 with the double arrow, what that indicates is that the forward reaction rate is the same as the reverse reaction rate. So I'm going to kind of write 2 rate laws each way. I'm going to write 2 rate laws for step 1, one for the forward and one for the reverse. The forward reaction rate law would look like this, K1 times NO times Cl2. And here, this is just something weird your book does. This is supposed to say K negative 1, and the 1s and negative 1s don't really mean anything. They just help us keep up with which step we're dealing with. So K1 is the forward reaction of step 1. K negative 1 will be the reverse reaction of step 1. So I can make this little equation actually using the idea that the forward and reverse reactions have equal rates. If you just do a little bit of algebra here, you can actually kind of solve for concentration of NOCl2. Algebraically, it would be equal to everything I've got over here on this side. So the trick is that I actually substitute in, here was NOCl2 in my rate law, and I take this whole term and just plug it in place of NOCl2. And then I do a little bit more math, and the one thing to say about this is that these K's, we never really care too much about all these K's. I'm just going to sort of glump them all together and say, oh yeah, there'd just be one giant K for the whole reaction. So K2, K1, doesn't really matter. Just blump all those together and call it K for the overall reaction. Here's an NO and here's an NO, so this is a 2, this is a Cl2. So basically what I've done is I've taken my step 2 slow step rate and I've sort of manipulated it a little bit until it includes substances that are reactants in the reaction. Remember, our original reaction, had NO and Cl2 as reactants. So if I want a rate law, I need to have a rate law that also includes NO and Cl2, and here it is. I've done that. So that little intermediate trick is something that you'll want to practice with a little bit. So here's another example. Let's say I have an overall reaction, this one that you can see here, and let's say someone has told me what the overall rate law is. This is again, maybe working with tables and powers and dividing and things like that. They've come up with the rate law that's first order in hydrogen and second order in nitrogen monoxide. So I know this is given. I've also been given a possible mechanism for the reaction, and here's a 3-step mechanism just to show you that there are such a thing. Each of the steps is shown. They're identified as whether they're fast or slow steps. This is a very typical question. If they're going to ask you something about a mechanism, it's probably going to sound like this. Is this mechanism consistent with the observed rate law? One thing that we're supposed to check really is to see whether or not these 3 reactions would add up in a Hess's law type of way. Do these 3 reactions add up and give me my original reaction? I'll let you just double check that and make sure that it works. It probably does. That's not what we're going to focus on right now. We're going to focus on the rate idea. In order to be consistent, this statement in red has to be true. The rate of the slow step for the mechanism has to be the same as the overall rate. We have to sort of prove that they match. So I write, here's the rate of step 2. Step 2 is identified as the slow step here. I write a rate law for step 2. It's K2, little k2, times N2O2 to the first power and H2 to the first power. I've got the same problem that I had before. I can't really say yes or no about this rate law because it includes this intermediate substance. N2O2 is an intermediate. I have to perform a little algebra type of math so that I can get rid of the N2O2. I can do that using step 1. It's another double arrow reaction, which means that the forward rate and the reverse rate are the same. So here's a rate law for the forward reaction, K1 NO to the second power. Here's the rate law for the reverse reaction, K -1. Similar to the other problem, I can do a little algebra here and solve for N2O2, and I get this expression right here. If I take that expression and I substitute it into this rate law, I'll get something that looks kind of like this. Remember that you can just blob all of these K's together into one, and so by the time I get done with this, I have the rate of the slow step says KNO2H2. And if you remember, that is consistent. It's in the other way around, but that doesn't matter. I have first order in hydrogen, second order in NO. And if I look down here at my finalized mechanism rate law, that also matches. So yes, that matches the overall rate.